Hello and welcome to my presentation on hardware attestation in TLS. I want to talk to you about how we plan to integrate remote attestation as a native authentication mechanism in TLS. But first off, I want to introduce myself. I'm Ionuț Mihalcea. I'm a senior software engineer in ARM, and I work in the system solutions prototyping team, essentially doing proof of concepts for various bits of code that we think are relevant to our software ecosystems, particularly around confidential computing. Let's get an overview of the presentation. So I'm going to start by talking about the theory behind remote attestation and TLS, at least the bits that are important when it comes to integrating the two, and also the standards work that we're doing to enable this. Then I'm going to be talking about the practical side and the prototype that we're trying to put together to showcase the standards work that we're doing and the various bits of software that are involved in the software ecosystem around it all. But first, let's start with the theory. Let's have a look at remote attestation in TLS in particular. First, what exactly are we trying to improve here? So the current status quo for security on the internet assumes an attacker is somewhere in the communication path between two endpoints. So we want to prevent this attacker from doing anything by essentially giving the workloads or the entities access to credentials and to certificates, so they can authenticate each other and then use that to bootstrap a secure channel, communication channel between them. And this is quite good, and it works, and it also needs to trust. You also need to trust your peer when this sort of solution is in place. You need to trust them that they deploy the correct software, that they're protecting their identity key, because if either the software has been deployed wrongly, either something malicious has been deployed, or perhaps someone has subverted security, or if the identity key has been extracted, then you can't really trust your peer anymore. So this trust is necessarily bound to the entity who's provisioning the workload. And if any hardware backing is actually used to protect any of the system, it's usually reserved for the identity key of the workload. But what if there are cases where we want perhaps more information, more transparency about the security state of our peer? Could we actually use more remotely verifiable information about the security state, about any software or the identity key that our peer is using? And the two use cases that have prompted us to look at this are twofold. So on one hand, we have an edge device trying to onboard to a service. So we have a device that has a pre-provisioned identity key, and we own both the device and the service, and we want to make sure that only our devices can connect to the service. So we assume that the edge device can then go ahead and use that private identity key to sign some attestation credentials that they can use to authenticate to the service. Now, on the other hand, we have a confidential computing use case that is obviously quite relevant for us today, and it involves a cloud workload that we're trying to authenticate, perhaps from a local device, trying to connect to that workload from a local device. And we want, again, the workload to authenticate using an attestation credential, again, signed using some pre-provisioned private identity key that resides somewhere within the server chip that's running that workload. So what is remote attestation and how can it help us? So remote attestation is a class of hardware-backed mechanisms and the associated protocols, which enable a relying party to have some cryptographically verifiable proof about the state of a previously untrusted workload. So the relying party can then check, for example, what software booted on the platform, what operating system is running, perhaps even what applications are currently running, and also what the workloads running on the platform, what identity keys they have, and how they're protected. And the attester device can do this using that pre-provisioned private identity key, which which it can use to essentially generate new credentials for all the applications running on top of it. Essentially, the attester device becomes its own certificate authority, and it can back itself using a certificate provided by the manufacturer from the factory. And to have a better understanding of what remote attestation entails and how it works, let's have a look at the data flow. So in this data flow, it's worth considering the fact that the arrows aren't actually physical communication paths and rather logical data paths. And it's important to keep in mind that the entity that is being authenticated is the attester. So the relying party is trying to authenticate the attester, but as you can see from the diagram, the communication is not direct, at least in this data flow, direct between them. And instead, there is an intermediary, the verifier, which consumes the attestation evidence produced by the attester and then emits attestation results after it appraises that attestation evidence. And the verifier does this by using a series of what amounts to a supply chain of metadata provided by the entities on the upper side of this diagram. And in particular, the endorser and the reference value provider are the ones who actually provision the device. So provision all the software that will perhaps help boot the device and will actually run underneath our workload. And they also provision the identity key. And with this information about the device, what software it should be using, what its identity is, I can then go ahead and endorse the device to the verifier. And the verifier can use these endorsements to compare them to properly assess the attestation evidence. And once this appraisal is done, the verifier can produce then attestation results that are valid and that the relying party can find trustworthy. We move over to our second protocol, to the transport layer security protocol. So TLS is a pretty ubiquitous component of network security. It allows application protocols to have confidentiality and integrity over a secure channel, and the secure channel is established following a Handshake protocol. And this Handshake protocol allows the two parties to authenticate each other. Let's have a look at how this actually works in practice. Let's have a look at version 1.3 of the TLS Handshake. The Handshake is started by the client using a client hello and a key share. And at the client hello, we can find a number of supported cipher suits and a number of other extensions that the client might wish to use as part of this handshake. The server then replies with its own server hello, for example, by including some chosen cipher suit, and replies to any of the other extensions that were provided by the client, and also its own key share, a certificate and a certificate verify message, and the finish message. The client can then also go ahead and authenticate itself if it wishes to, or if the server has requested it. So it can then send a certificate message, a certificate verify, and a finish message. And once these free flights are done, the two parties, the client and the server, share a secure data channel. It's worth keeping in mind that from the second flight onwards, most of these messages are actually encrypted. And this helps with some of our privacy considerations because the certificate message is being encrypted. Passive fingerprinting is at least partially mitigated. The components that we leverage to allow remote attestation to be used as an authentication mechanism are the extensions and the certificate messages. The extensions are used to carry across a negotiation part. We allow the client and the server to negotiate what attestation schemes or what attestation result formats might want to be used, or perhaps if the attester is the one communicating with the verifier, which verifier to have produced the attestation results that will be carried in this handshake. And the certificate messages are then used to actually carry the attestation credentials. And these attestation credentials can be carried in the certificate message either alongside X509 certificates or instead of the X509 certificates on their own. And an important question to answer here is why TLS? Why would we want to integrate at this level? At the moment, remote attestation is mostly done on top of TLS. So once the TLS secure channel has been established, the two parties run a remote attestation protocol on top of that. And we believe that by combining the TLS handshake and the remote attestation, we can actually have an improved performance, since we don't have to serialize the two protocols, so they can be run essentially in those free flights in the TLS handshake. And also it gives the attacker a smaller attack surface because they can't even establish a secure channel to their victim device. And also we want to integrate remote attestation in the TLS layer because it makes it easier for application developers at a higher level to consume remote attestation. And because by including this remote attestation as an authentication mechanism in TLS, application developers only need to establish the TLS connection, and then they have both the guarantees of remote attestation and those offered by the TLS handshake. Our goals here obviously are to enable authentication via remote attestation in TLS, but more broadly, we also want to support the most common deployment patterns. So for example, whether it is the attester's job to communicate with the verifier and exchange attestation evidence for attestation results, or whether the relying party is the one supposed to communicate and to have a relationship with the verifier and to exchange the attestation evidence for attestation results, or perhaps whether users want to use to make use of remote attestation on its own in the TLS handshake, or whether they want to somehow pair that with PKI with an X509 certificate. We also want to support a wide range of attestation schemes and formats. So we want to support as many backends, as many roots of trust as possible, everything ranging from TPM 2.0 to perhaps ARM's confidential compute architecture. I want to support as many attestation result formats as possible. More broadly, we also want to abstract away all this heterogeneity of attestation schemes. We don't want application developers to have to deal with the messy low-level behavior of the platform that they're trying to attest, and instead to simply you use remote attestation in an abstract or easy-to-consume way. In terms of security, obviously, since we're introducing new TLS extensions here, security is of utmost importance to us, and we're planning to formally verify these extensions. But in the meantime, we're also planning to, and we are meticulously working to prevent any attacks. For example, in the cases where we combine X509 certificates and attestation credentials in the same handshake, we want to make sure that neither of the two credentials can actually be relayed or spliced. And in terms of privacy, we do realize that attestation credentials can reveal a lot of privacy and security relevant metadata. And the asymmetry of the TLS handshake, where the server always has to show their credential first before being able to authenticate the client, can lead to perhaps an attacker finding out a lot more about some of the workloads or the platforms that they're running on than we would need. So for example, an attacker can leverage this to find out what operating system some device is using, and then to leverage this information to use some exploits that already exist for that version of the operating system. But we're trying to at least partially mitigate this by allowing negotiation and allowing the tester to choose to use privacy-preserving attestation schemes, or perhaps to use some privacy-preserving attestation results, which would involve, for example, redacted attestation results. Moving on to the actual practical side, the prototype that we're trying to build. And the big picture here is that we are trying to build an end-to-end proof of concept of this entire stack. So going all the way from the root of trust to the verification service, obviously going through a TLS implementation. Unfortunately, because because our theoretical work and the standards that we were putting together allow such a broad range of deployment patterns, we've decided to make our prototype simpler, to simply target the prototype to a specific deployment pattern that I'll be detailing in a second, and to couple this with a TPM 2.0 root of trust to back it all. And this is quite relevant here, given that many confidential computing use cases use TPM 2.0 interface as their backing mechanism. We're also planning to open source the entire stack, not just because the software components that we're using are themselves open source software, but also because our work is harbored under the CCC Attestation 6, so under the Confidential Computing Consortium Attestation Special Interest Group. And some of the components that we're using are also part of the Confidential Computing Consortium or the Cloud Native Computing Foundation as well. So having a look at the architecture of our prototype and trying to view it perhaps through the lens of that remote attestation data flow diagram that I presented earlier. We have here the three main components that we're trying to use. So we have on the bottom side, we have an attester that has a root of trust, and this attester trying to authenticate with a relying party on the upper hand of the diagram. And this relying party has a relationship with the verifier, and it communicates with the verifier to appraise the attestation evidence that it gets from the attester. To put more details into this diagram, so the attester now becomes a TLS client, the relying party becomes a TLS server, and the components involved are on the client side, we have embed TLS serving as the TLS stack, and embed TLS is interacting with the root of trust, essentially gathering attestation evidence using the Parsec service. On the relying party side, we have again embed TLS, and on this side we have embed TLS communicating with the verification service built using Verizon. So now I want to talk about a bit more about all of these components, starting with the one closest to the root of trust. So starting with Parsec. Parsec is a platform abstraction for security. It allows cloud-native applications to consume hardware-backed security services offered by the platform that they're running on. And the Parsec service does this by running in user space and providing an easy to access and easy to use interface that's easy to use from any programming language or runtime. And the core goal of Parsec is to allow these applications to provision an identity key for themselves and to use that identity key. So they can provision, for example, a cryptographic key pair in a discrete TPM, or perhaps in a remote HSM or some trusted services running in Trust Zone. And then they can use these through Parsec. As part of this project, we've expanded the APIs and made them easier to consume. The APIs around attestation, so that now cloud native applications can also consume quite easily and through an abstracted API to be able to generate credentials either for their identity keys or perhaps attestation for the platform that they're running on. Moving on to the other side of our prototype, where we have Verizon. So Verizon is a library, an open source library of components that can be used to build an attestation verification service. So these components can allow you to assemble everything from an endorsement or a verification API, or any number of plugins that allow you to appraise various attestation schemes. In this diagram, you can see a manufacturing plant producing a device and using that information it has about the device to endorse it to the verification service once this has been deployed. And once the device is in the field and it tries to attest to some application or to some service, that application or service can then query the verification API and provide the attestation evidence it got from the device. And the verifier service can use the attestation evidence it just got and the endorsement it got from the manufacturing plant. It can appraise that evidence and produce an attestation result that the application or service can use to determine whether it trusts the device or not. At the core of our prototype is, of course, the TLS stack, and we've chosen Embed TLS mostly because of our previous experience with it. And Embed TLS offers an implementation of the TLS and DTLS protocols, and it also provides a reference implementation to the PSA cryptography API. And we've used this PSA cryptography API as a route to easy integration with Parsec, essentially. But in the future, on the TLS side, we do hope to also have an interoperable OpenSSL implementation that we can use so that perhaps the client and the server can use different TLS implementations and showcase our work better in that way. Going back to our prototype architecture diagram, I just wanted to emphasize the fact that we have this goal of trying to make remote attestation very easy to use as an authentication mechanism in various protocols. And this does involve the fact that authentication has to be orthogonal to the rest of the protocol. And in our case, this happens for TLS, and we leverage this in TLS. But you can easily envision the same thing happening or being used for example, a quick stack, or really any protocol where an application is trying to authenticate a device. It might want to do so using attestation, remote attestation, to do that authentication step. And in the context of trying to use attestation essentially as a plugin for authentication, we think there are a few requirements that we're essentially trying to fulfill here. So first off, it must be really easy to integrate the applications, the higher level applications, for both the tester and the relying party. And we believe that we're doing this quite well with Parsec and Verizon both being developed essentially and designed essentially to allow cloud native applications to easily access these services. The second thing that we're trying to achieve is that we're trying to have a composable design that is essentially ideal for adding new attestation schemes or perhaps migrating between existing attestation schemes. And the modular nature of both Parsec and the Verizon service allow them to expand and extend in this direction quite easily. And last but not least, any work in this field must be done with some proper tooling to allow easy prototyping for higher level applications. So what we're trying to do here is that we are trying to provide a containerized environment that essentially simulates the end-to-end root of trust to verifier, which can be easily spun up and easily used by higher level developers to perhaps try to plug in remote attestation as an authentication tool. So just to wrap up here, we do believe that remote attestation is a viable authentication mechanism for TLS, and we're trying to standardize this and make it as easy as possible. Our design aims to be as flexible and secure as possible, and this includes both the standards work that we're trying to do and the practical side, the prototype. And we want to also reify the theory that we're trying to put in those standards into an end-to-end prototype that other people can look at and perhaps use for their use cases. So we're hoping that the prototype that we're building will serve as a model for integrating remote attestation and perhaps other protocols. And I'd like to end here and ask, are there any questions?